This video covers the assembly and alignment of a gas laser with external optics. The laser is a Melles-Griot helium-neon laser with external optics. Unlike a regular helium-neon laser with mirrors fixed directly onto the tube, this one has optics which can be aligned. This being the OC and this being the HR. Now in order to accomplish this, the tube itself must be sealed. The ends of the tube are sealed with windows. These windows, one there and one there, are specially coated with an anti-reflective coating. A normal piece of glass, if used as a window, would logically lead to a 4% loss per surface. Consider that the beam inside this laser goes through 1, 2, 3, 4, 5, 6, 7, 8 surfaces. 8 surfaces times 4% per surface is a very, very large loss, and one which would never allow this laser to operate. So we have very, very special windows on this tube which are extremely low loss. They're coated with what's called a V coating, which is an extremely high performance anti-reflective coating. So we have an amplifier in here with XA and XG like any other. You have an HR at this end and an OC at this end. And the purpose of this video is to show you how to construct and align these optics. Here we see the components of the helium-neon laser that we're going to construct. We have the helium-neon plasma tube itself. It's a typical plasma tube, very similar to anything that you'd ever find in a helium-neon tube, except with windows at either end. These are the actual separate optics, the HR and the OC. Those optics will be mounted on posts on either end. Tube holders will hold the plasma tube. And finally, the power supply and the power supply cable. The cable itself has a ballast resistance in it, necessary because of the electrical characteristics of the gas discharge itself. We begin then by installing the actual optical mounts on the breadboard. The post over here is going to be for the OC. The post over here is going to be for the HR. These posts over here are used to hold the tube holders. Now the tube holders are very simple. They are clamp type mount. You put this bar across the top and you simply clamp it gently to the tube. I'll lay the tube into the holders now, like this. That's the anode end, the high voltage end. I'm going to be very careful to put this towards the HR. The reason is I'm going to line up the HR first. Once the HR is lined up, I'm going to leave it alone. I'm going to leave the space in here for an intercavity experiment. This is where my glass slide is eventually going to go, so I can use it as an intercavity loss. To mount the tube, we clamp the bars on like this. And gently tighten in the two clamps. The tube is now affixed. Now the actual HR over here, very simple. There it is right there. There's a hole in it. And we'll mount that onto this post right there. All right. Zooming out, we can show you the process of bore sighting. This is a very important thing. What we're basically going to do is ensure that light can go all the way through that plasma tube, go through the dead center of this HR, and then bounce off of it back in. Obviously you can see right here that the HR is too low. How high do I need to put it? That's what this process of bore sighting is all about. So I'm going to begin by putting a lamp right here. There's a fluorescent, just a CFL, any type of bulb works for this. And then I go to this end and I raise it up carefully until I can see all the way through the tube. And sometimes it helps if you block the light a little bit like this, and you can actually see right through the bore of the tube. Now I've got the height correct, but it should move over a hair, and that's easy enough to do. There's a washer on this mount over here, which allows me to move it horizontally. So I move it ever so slightly horizontally, and now I can see down the entire bore of the tube. I can see where I'm blocking the light. It gives me a clear shot all the way through, hitting dead center of the mirror and back. It's also very important that I do get dead center of this mirror, because dielectric mirrors like this have a sweet spot, if you will. The actual dead center of the mirror is highly reflective. As you move away to the edges of the mirror, the reflectivity suffers. The reasons for this are mechanical. It's due to the way you manufacture a mirror like this, and we will actually look at those type of mirrors in another course in the program. Looking through the HR itself, you can actually see the view as you bore sight. You can see it's blue. It's blue because the mirror reflects red light and transmits blue very well. So the actual light from this fluorescent tube over here is traveling through the plasma tube bore, hitting this mirror and bouncing back. At least the red light is. The blue that you see is being transmitted. And if you look through the optic very carefully when you're bore sighting, and I'll zoom in, you can notice that as I block the light with my finger, you can see the actual light going through the dead center of that tube. It is lined up correctly. If you can't see through the actual tube itself completely, stop, because there's no way this thing is going to work unless that mirror is lined up dead on. The next step in the alignment is to set up what's called an autocollimator. Now, an autocollimator is a very simple thing. Light from this lamp goes through a beam splitter, and this is just a regular, normal beam splitter. The light goes through it, goes through the tube, bounces off the HR, goes back through the tube, bounces off the beam splitter, and you put your eye right here and you look through the tube. Obviously, the tube is turned off when you do this. What you see is a reflection from this mirror. And when you first do this, you'll usually see nothing, in which case you start to crudely align this mirror, and eventually you'll see a red or an orange dot, and that's the reflection from this mirror. What you want to do is optimize that dot so that you've actually got a round concentric circle inside the plasma tube itself. So you're looking through here, you look at the actual glass plasma tube, and you see the glass, and you see a little orange dot. You line it up so you get a perfect orange dot in the center. If you see a half moon type pattern or something like that, it means it's total internal reflection from the tube walls itself. If that happens, the laser will not work. So the end game here is to get this mirror, the HR, absolutely 100% perpendicular in both directions to the plasma tube bore itself. And here is a view through the actual autocollimator itself. You can see the lamp, the beam splitter, and the plasma tube over here. What I'm going to do is zoom in a lot, and you'll be able to see, now you can start seeing the actual image of the tube itself in there. Alright, see that little image of the tube? There's the actual front of the tube itself, and you can see the image of the tube right there in the beam splitter. Alright, so if I start moving this around, the actual optic, you'll notice that little reflection. There it is right there. It's blinking right now because I'm moving the actual optic. That's the reflection from the HR. So what you do is you optimize the HR to make that little tiny dot as round as possible and completely concentric within the actual plasma tube itself. And here's a view of the actual concentric. If you get something like this, it's total internal reflection from the tube. You can see it's a half moon type pattern. Once again, this is approximately what you're looking for. A nice bright orange dot that's 100% concentric within the actual plasma tube itself. At this point, the HR is completely aligned. You can remove the beam splitter, put in the output coupler, and align it. From here on in, do not touch the HR. It is very, very important. From here on in, Do not touch the HR. It's aligned as well as you can do. We'll do a final alignment on it later when the actual laser is operating. As with the HR, once you install the OC here, you have to line it up by bore sighting it to ensure that light from the laser tube itself goes right through the dead center of that mirror. In order to complete this operation, I placed a fluorescent lamp at this end so that the light from that lamp goes through the HR, all the way through the plasma tube, and then hopefully through the OC. And we simply move the OC up and down until we can see right through the dead center of the plasma tube. At this point, everything is lined up in the same optical plane, and the only thing we're left to do now is to line up the OC. Now, in reality, we could use another autocollimation procedure. In other words, we autocollimate the HR first, and then we reverse the process and autocollimate the OC. But in this case, we're going to use a different procedure called the rock and bump procedure. It's a procedure in which you literally rock this mirror, sweeping it in a known pattern until it oscillates. It's a very simple procedure. It's used commercially in lasers oftentimes where you have to replace one optic only. The final step is to line up the OC. And as I said, this is done by the rock and bump procedure. Basically, it's a sweeping procedure where you sweep the reflection from that mirror onto the tube face until finally it lines up, at which point you get a blink over here on this white card. I'll turn on the laser now. I've wired up the positive, the high voltage lead, to the anode, and I've wired the negative to the cathode over here. Turn on the laser and allow it to do its startup. Now, I'll show you afterwards what it looks like on the cathode itself, but there's a reflection, a very weak reflection of the spontaneous emission from the output of this tube onto the cathode itself. And what we do is set that spot to be too high and a little bit off to one side. And now I rock the mirror. And what that's doing is sweeping the beam up and down. Now the beam is too far towards me right now, and it's sweeping up and down. And as I do this continuously, I slowly rotate the horizontal adjustment on the kinetic mount on the mirror, kinematic mount on the mirror, and eventually, and this is a very, very slow process, you do it extremely slow, eventually you'll see a little tiny red dot appear, and that means the laser is oscillating. There's my blink right there. You see that little blink up there? Every time I sweep this up and down in this direction, I'm lining it up. So the horizontal is lined up now. Don't touch that one. Take the vertical adjustment right here and slowly move it until you have a continuous, there it is right there, continuous laser output. At this point, it's simply a matter of what's called tweaking the mirrors until you get them exactly lined up. You see, right now they're lined up with each other. There's no other way this laser could oscillate. The HR and the OC are perfectly parallel to each other. The problem is the tube in the middle is probably cockeyed. In other words, we're only using a small portion of the actual amplifier's volume. In order to optimize the power of this laser, not only do I need these to be parallel, but I also need them to be 100% perpendicular in both directions to the plasma tube itself. And so what I'm going to do is use a process called walking the mirrors, in which case I move the mirrors like this, in one direction, then the other direction, until finally I get optimal output power. For this, I'll need a power meter. Now before I go any further, I should show you the actual sweeping procedure. You'll notice I have the mirror right here, and that's the OC, and there's a reflection right there at the end of my card. Now that reflection, here, if I move the actual mirror, you'll be able to see it. That reflection moves up and down. Now what I've done is I've set it too high. In other words, I've set it to sweep at the very, very top, and then what I'll do is I'll move the camera a little bit here. Okay, so you can see the actual beam, or rather the reflection from the tube, sweeping. And then what I'm going to do is I'm going to rotate the horizontal at the same time so that not only is this reflection sweeping up and down, but it's also sweeping inwards this way. And eventually I get it to laze. So let's try that operation. I'm sweeping up and down now, and at the same time I'm ever so slowly moving the horizontal adjustment. And there you go, you can see that little blink of light. Once again, at this point, the horizontal is lined up. It's only the vertical that has to be adjusted. So I take the vertical at this point and move it down so that that reflection moves down on the cathode until at some point it oscillates continuously, like that. A small adjustment of either mirror optically just to give me the maximum power, and at this point it's time to get a power meter to completely optimize this laser. Well, the laser is now oscillating, and it has a total power output from the OC of about 800 microwatts. It's rated for a lot more power, and what we need to do now is completely align the mirrors, that tweaking process that I talked about. And all we're going to do is get a lot more power out of it by ensuring that the mirrors are 100% perpendicular to the tube. Easy enough to do with this procedure. You do it to the verticals or the horizontals, never both at the same time. So I'm going to start with the horizontal axis. You take one end, the horizontal adjustment, and you turn it a little bit. So I'm going to turn it about 1/8 of a turn in one direction at random. And you'll notice the power is starting to climb. Now I let go of this, don't touch this one anymore. Take the vertical on the other side and optimize the power as high as you can get it. And it looks like I'm getting about 3.4. Okay, so I've gone too far. I'm going to optimize as much as I can get, about 3.5. There we go. I'm going to turn this optic a little bit more on this end, and then power goes down. And now what I do is I optimize the maximum output power I can get. It's starting to climb again. 2.8, 2.9. 2.9 was all I could get now, which means I've gone too far. So I'm going to turn this back to where I was, where I had the maximum output. And once again, I'm going to optimize for as much power as I could get out. It's climbing slowly. 3.3, 3.5, 3.6. That's about as high as I can get, about 3.6 milliwatts. Now I do the exact same process with the other axis, in other words, the vertical axis. Once you've done the horizontals, leave them alone, do the verticals. So once again, I'm going to turn this at random, about 1/8 of a turn in this direction. I don't ever really know which way I should turn it, just kind of randomly select one. And then I'm going to optimize the power, 4.1. Oh, so I was going up in power, 4.2. It means I was going the right way. So I'm going to turn it a little bit further. And then I'm going to optimize the power again, 3.5. Oops. So about 3.5 is all I could get here. Not as much as I had before. So I'm going to take this vertical control and go back a little bit where I was and optimize for maximum power. 4.1. 3.5. You notice how touchy it is. Even by letting go of the knob, it changes the actual alignment. Lasers are extremely touchy when it comes to alignment of the mirrors. It's one of the reasons why we have to use such large, heavy frames to hold these two mirrors. On a commercial laser, you'll oftentimes find both mirrors mounted on a very large metal frame with 3 rods going through it to keep them from twisting. Now I've done the horizontal, and then I did the vertical, and I went from about 800 microwatts to 4.1 milli, well in this case 3.8 milli. Let's go back to the horizontal. And once again, align it again. Go in the one direction, and we try to get a little higher power out of it. And I'm not getting higher power, so I'm going to go the other way with this one. Let's see if that helps. Maybe a little further. All right, we'll go back to where I was. I was already fairly well aligned, apparently. Oops, 3.5, 6, and then do this direction again. And when I've maximized my power output, I'm happy with the alignment, that's it, the laser's done. At this point, the laser is fully aligned. I've optimized my output power. In the next part of this video, part 2, we're going to look at experiments that you can do with this laser in terms of observations of modes and inserting an intercavity loss right into the cavity in order to measure the gain of the actual laser itself.